Great. Well, it's such a pleasure to be here. This is one of my favorite events that iQuHACK and the Center for Quantum Engineering put on each year. And, very pleased to have been invited to tell you a bit about quantum computing and introduce it. People here are probably from a range of backgrounds. And so let me tell you basically how I look at quantum computing and introduction. It's not too long, but this is how I like to think about it. You've probably seen this picture before. Usually it's in black and white. I found one that's in color. This is a Solvay conference in 1927. Many famous people in here. We call this Quantum 1.0, or the first quantum revolution. It's when we first developed and understood quantum mechanics and how things work at the small scale. If you look in there, 17 of the 29 attendees ended up winning a Nobel Prize. One of them, Madame Marie Curie, actually won 2 Nobel Prizes. The development of quantum mechanics obviously was very, very important. And it was partially important because it laid the foundation for what became classical electronic computing in the 20th century. And that, of course, had tremendous impact on our economic security and where we are today, as well as our information security. And it's not just electronic computing, it's also lasers and whatnot, but let me just focus on classical electronic computing. The vacuum tube was invented in 1906, and it was used for radio transceivers for many years. It was 40 years before it became finally the logic element in a computer called ENIAC, developed at the University of Pennsylvania, and that was around 1946. And the following year, the transistor was invented at Bell Labs. And here's where quantum mechanics comes into play. Because it was through quantum mechanics that we understood the band structure of semiconductors. But once we knew that, we then made this thing called a transistor, which is basically a switch. It's a classical device. It doesn't use quantum mechanics in any fundamental way, but we needed quantum mechanics to understand how it worked. So within about 10 years from that development, we had a computer that's called TX0, or TIXO, developed here at MIT. You can see it takes up a whole room. And it doesn't look like the computers we have today in the sense that those transistors were basically soldered together. To get closer to where we are today, we needed integrated circuits. That came in the late 50s, but it was still another 20 years before we got chips like the Intel 4004, a 4-bit processor in the early 70s, used in calculators. And yet another 20 years to get to the Pentium Pro. I remember using Pentium Pro computers with millions of transistors in the mid-90s. And then fast forward another 25 years to where we are today with GPUs and CPUs, and now approaching 100 billion transistors on a chip. So compared with that, quantum computing is quite nascent, right? In the early 1980s, late 70s, early 80s, people like Richard Feynman, Yuli Manin, and others suggested that, look, if you want to simulate a quantum system, you actually need to use quantum mechanics to do that. And people thought about this for a good 10, 15 years, and then started to come up with some algorithms that could actually use this idea if we could build the hardware to do it. And one of them, you'll hear from later on the panel, Peter Shor, came up with the famous Shor's algorithm. And he and his colleagues, Kohler, Bank, and Steen, came up with quantum versions of error correcting codes that are going to allow us to ultimately one day run algorithms at scale. Eddie Farhi, also here in the audience, adiabatic quantum computation. Nishimori in Japan, quantum annealing. And by 2000, people like Ike Chuang, also a professor here at MIT, while he was at IBM, actually demonstrated Shor's algorithm and showed that 15 is equal to 3 times 5. Okay, it seems silly, right? But we know it works. We know it works. And when we can build a quantum computing hardware large enough to do it at scale, and importantly at a commercializable scale, that's when we realize the full promise of quantum computing. Since then, it's been 20 years, and where we are today, well, we'll hear from some of these panelists, we actually have quantum computers. They're just small, 50, 100, few hundred qubits. But the progress has been tremendous. You can even access them online, many of you will, and we hold hackathons now to learn how to program them. So the takeaway message is that quantum computing's real. It's happening right now. It's transitioning from a scientific curiosity to a technical reality, okay? It's going to take time. Like, look at that timeline for classical electronic computing, right? It's going to take time to get there for quantum computing as well. We know that. But the reality is you've got to be in the game if you want to play. There's no surprise that the companies that are building those large 100 billion transistor chips today, they didn't get into it yesterday when someone else figured out how to do that. They got into it decades ago. You've got to be in the game, and that's why I'm so happy that so many of you are here getting in the game, and you're showing us how we're going to program quantum computers in the future. So just a brief intro to quantum. How is a quantum computer different? I like to compare it to classical computing, because I'm an electrical engineer. That's how I was trained. Classical bits, transistors, a voltage on a transistor. It's either there or it's not. It's a switch. It's digital 0 or digital 1. That's it. These are discrete states. Quantum computers use quantum bits, or qubits as we call them. And we think of it as something called the block sphere, or you can think of it as the planet Earth. And if you're at the North or the South Pole, then you're just in one of these classical states, 0 and 1. You're basically a transistor. But of course, we can be anywhere on the surface of the planet Earth. We don't need to just be at the North or South Pole. And when you're anywhere other than the North or South Pole, you're in what's called a quantum superposition of 0 and 1 simultaneously. What's important about this is that this is not classical superposition where you can actually keep track of both at the same time by measurement, right? This is a quantum superposition. You are standing at one place on the Earth, let's say on the equator. You're at one place. You're not in two places just added together. You're at one place. But that one place has aspects of both 0 and 1 simultaneously. And it's weird, but that's quantum superposition. So quantum computers encode information in qubits, and they behave fundamentally differently than classical bits. So one consequence of this is how we can view, say, n qubits, or n, let's start with n bits. If you have a conventional classical computer, and you have n bits, you can form one n-bit number, 2 to the n. It's exponentially large, that state space, but you can only form one of them at a time. So if n is 3, you have 3 transistors, you can form one of 8 different states, 0, 0, 0, or 0, 0, 1, etc., all the way up to 1, 1, 1. And so if you want to process, for example, all of those inputs and see what the outputs would be, you basically only have 2 choices, right? You represent them one at a time, and you feed them into the same computer serially in time, and you get the output. Or you buy an exponentially large amount of hardware, and you do it in parallel. But either way, it's going to take exponential time or exponential hardware to do this. With a quantum computer, it's n qubits now, and that same 2 to the n exponentially large number of classical states comes in. But the difference is you can put them all into a single superposition state. And then we feed that into a computer, and the quantum computer will then provide an output. Now, when we measure that output, something's going to happen. We're going to see that in just a moment. But for the moment, this is representing quantum parallelism and, importantly, quantum interference to make this happen. So how do we take advantage of this? Well, again, let's think through classical Boolean logic. We know that we have some large state space, and we start in some point in that state space, and we want to be able to get to any other point in the state space in order to perform a computation. And the way that we do that is using Boolean logic gates. And they can be either single-bit gates or 2-bit gates. And you can see some examples here. I won't read through them all. The NOT gate, the AND gate, the OR gate. What's important, though, is that you don't need all of these gates. You don't need the 3 and the 4 and the 5, etc. You can form a universal set of Boolean logic gates with just a handful of these. And it's not unique. There are different combinations that work. It's important to note you need at least one 2-bit gate to do it. Quantum mechanically, it's the same story. We have a large number of single qubit gates, which are basically rotations, movements around the planet Earth in different ways. And we also have 2 qubit gates. And in the 2 qubit gate case, usually it's conditional in that something happens to qubit 1 depending on the state of qubit 2. But the point is that you can form a universal set of gates with just a handful of these single and 2 qubit gates. And it's not unique, right? You can form different sets. One difference is that quantum gates are reversible. Now, there are some cases of classical gates which are reversible as well, but all quantum gates are reversible. And it does require, again, at least one 2 qubit gate, and it needs to be what's called an entangling gate. So let me just give an example of a single qubit gate. And its analog is the classical NOT gate. We're going to call this one the X gate. It's a rotation around the X-axis. This is what it looks like. So we're on the planet Earth. We start at the North Pole. And then by applying electromagnetic pulse, we're able to rotate from the North Pole down to the South Pole. We call it a pi pulse because we're rotating 180 degrees. And we call it an X gate because we're rotating around an axis that we call X. So we take state 0 to state 1 to state 0. And the way it is here, this is really just a classical gate, because we started at the North Pole, we end at the South Pole. But we could start anywhere on the surface of the Bloch sphere. We don't need to start at the North and South Pole. And then when we start anywhere else, we're starting in a superposition state, and we end in a superposition state. We're still rotating by 180 degrees around the X-axis. And you can see that what this X gate does is it swaps the coefficients alpha and beta in that superposition state. Okay, so this is an example of a single qubit gate. We'll now look at a 2 qubit gate. This one's controlled NOT, and its classical analog is the exclusive OR gate, where you have 2 bits, X and Y, and then you apply this exclusive OR operation. And you can see from the truth table that's shown here, I guess there's one way that you can think of this, is that one of these is a control bit, and the other one is the target. And when the X bit is 0, we just pass the target to the output, 0 to 0, 1 to 1. But if X is in the 1 state, we're going to swap the target. 0 becomes 1, and 1 becomes 0. That's a classical exclusive OR gate, or one way to look at it. And the controlled NOT gate is exactly that, and the truth table is exactly the same, except we now use quantum notation. So the rotation of qubit Y depends on the state of qubit X. And this leads to some very interesting conclusions. For example, if you start with, say, this X qubit in a superposition of 0 and 1, and that's the control, and the target is in state 0, that's Y, you can see that at this point they're separable. But we can use linear algebra to calculate what happens. We'll take them one at a time. So this portion indicated by the blue line, well, my control's in 0, so I just pass the target to the output. But when my control is in 1, I need to flip the output, and now this is no longer separable into something that looks like qubit X crossed something that looks like qubit Y. And in fact, this is an entangled state. It can't be factored, and we would need to prove that it can't be factored in any basis to make this statement, but that is true in this case. And that's why the controlled NOT gate is, in fact, an entangling gate. So these are just 2 examples of the gates that you'll be using in the hackathon, of course, but universal gate-based quantum computation is achievable with just a small set of these gates. So then you could say, well, how does an algorithm work? And generally, we start with some input state. Often it is a massive superposition state of all of these classical aspects. And then you feed it into a computer that's running an algorithm, the algorithms that you're going to generate. And what an algorithm is it's a sequence of single and 2 qubit gates. You decide which ones and in what order to achieve some goal. The important thing to see here is that you'll apply a single qubit gate, you'll apply that gate to a single qubit, but what you see is that it impacts all 2 to the n classical aspects. That's followed by quantum interference. And what you see is you've applied one gate to one qubit, in this case qubit number 3, but I just changed 2 to the n coefficients. I modified them. We'll apply, of course, entangling gates, 2 qubit gates, and the same thing happens. You apply that to just 2 qubits now, but you affect all 2 to the n coefficients after some quantum interference. And generally speaking, the goal at the end of the day is that all of the weighting or probability amplitude, as we call it, should sit in front of one of these, or a countable few, of these classical states that encode the answer to your problem. And the reason is that we know when we make a measurement, we're going to project. And we're going to project out only one of them. But you could then say, well, with what probability do I get any one of those? And that probability goes as the magnitude squared of that coefficient. So if this is close to 1, or ideally even equal to 1, then with 100% probability, I'm going to measure that state, 0, 0, 1. And 0, 0, 1 encodes the answer to the problem that I posed. Okay. Now, developing this algorithm, of course, is quite tricky, and that's what you're going to do in the next few days. There are lots of algorithms that we have, and I won't read through the whole chart, but you can see the major categories include simulation, factoring, sampling solutions to linear systems of equations, optimization, search, and they have a classical time, meaning on a classical computer, as well as time on a quantum computer, the expected speed up. And of course, we're still doing research, right? We're still trying to improve these algorithms and understand better how they work. So you could ask, well, what does it take to have commercial advantage of a quantum algorithm? Well, very simply speaking, it takes 3 things. First, you better not have a good classical algorithm that solves your problem, because if you do, these computers are really fantastic. Just use a classical computer. You then need to have a quantum algorithm. There are lots of problems that are hard on a classical computer, but we don't know the quantum algorithm to solve it. Please help us and find more, but you need to have one, right? And then the third thing is, ideally, it should be a useful problem if it's going to be commercializable. We have a number of examples, like Deutsch-Jozsa algorithm, of problems which are mathematical in nature and, in fact, do exhibit quantum speed up on a quantum computer, but we haven't yet figured out how we're going to use that in a commercial sense, right? So we want to target algorithms that are commercially useful. And so this overlap region today is rather small. We would like it to get bigger, and that's part of the reason we hold hackathons like this, is to try to make it bigger. And there are 2 types of quantum advantage that we can get from these algorithms, represented by this formula. There's a polynomial in front, a to the n, and then an exponential where you have n now upstairs. If you change the prefactor, that's often called a polynomial improvement in the jargon. And that's, for example, taking n to square root of n. And that's a Grover type speed up. The other one is exponential, and that's where we really gain. And so what that encompasses is taking n in the upstairs and bringing it downstairs. Okay, when you can do that, that's a tremendous improvement in computational complexity. We don't experience this type of improvements in our everyday life, and so I have an example here that maybe you've heard of, and it has to do with pennies and getting paid a salary. Many of you are graduate students and probably feel like you get paid pennies as salary. But this one actually would be good. So imagine that I say to you as your advisor, I'm going to pay you differently this month. On the first day, I'm going to pay you 2 to the first power pennies. And on the second day, I'm going to pay you 2 to the second power pennies. And on the third day, 2 to the third, et cetera. And then I'm going to ask you, at the end of the month, would you rather take the pennies or $10 million? All right? And if you're like me, you start thinking, okay, well, that's 8 pennies, 16, 32, 64, $1.28. I've already got through the first week, and I've only got $1.28. And so you might be inclined to take the $10 million. But of course, that would be the wrong answer. Otherwise, this isn't interesting. And it turns out that just on the 31st day, you would get $21 million worth of pennies. And this illustrates the power of exponential growth. Another way to look at it is to ask, if I wanted to simulate a quantum computer on my classical computer, how big a classical computer would I need to just store all that information? So if you have about 30 qubits in your quantum computer, I could probably simulate that on a laptop. I have enough memory to store all of those coefficients. Go to 50 qubits, though, and now you need a supercomputer, maybe something in the top 500. Go to 80 qubits, and now you basically need all the computer resources on the planet Earth. Go to 160 qubits, and now somehow we need to use every silicon atom on Earth, and every silicon atom itself has to be a memory element. And of course, by 300, we know that this is larger than all of the atoms in the known universe, right? So this is another way to think about exponential growth. So it sounds great. Why don't we have quantum computers at scale right now? Well, it comes down to two time scales, and one is called the coherence time. And this is the qubit's lifetime due to either decoherence in the environment or control errors. And the way to think about it is you can set your qubits into some state at time t equals 0 and it's exact. Let's say we can do that perfectly. But from that point forward, immediately it starts interacting with its environment. Of course, we're also interacting with it. We're trying to implement an algorithm on it. But unbeknownst to us, or we may know that it's happening, but not the details of how it's happening, it's also interacting with its environment. And over time, you can think of it as this state blurs and eventually decays. So in my algorithm, I'm trying to go from this point in state space to this point, but due to the environment, it's actually going somewhere else that I don't know. And when those 2 points aren't close to each other anymore, I've lost track of my quantum computer, and that's decoherence. So the time scale over which that happens is the coherence time. The second important time scale is the gate time. How fast can I do these gates? Because you might imagine a good figure of merit is, I've got this much time to run my algorithm, how many gates can I do in that time period? And the faster I can do my gates, the better. So it's this figure of merit that's important. Be aware that long coherence times are not the only thing that we want. And you can think of this as a crazy example would be neutrinos. Would a neutrino make a good qubit? No, because a neutrino may have an infinite coherence time, but we can't control it. It also takes forever just to do a single gate. We can't even measure it, right? It's very, very difficult. So it's not just long coherence times. It's also gate times. And so with this, we can compare different qubit modalities against one another. There are lots of candidates, right, for the physical hardware. And what you see on this left axis is this figure of merit, and that's basically the number of operations before an error, and that's 1-to-1 in the gate fidelity over here. So if it's 1 error in 100, that's roughly 99% gate fidelity. If I have 1 error in 1,000, that's 99.9% gate fidelity. But importantly, we know speed's important too. And so this axis is the gate speed in hertz. Think of that like your processor clock. And so what you see are many of the leading technologies here, single and 2 qubit gates and where they fall. And the best performance, of course, is in the upper right corner, and you can see nobody's there, right? And that's why, we're all still working really hard to make these quantum computers work. Now, generally speaking, trapped ions are trying to make their gates faster. Of course, everybody's trying to make higher fidelity gates. And superconducting qubits were pretty fast. We're trying to get higher fidelity. And neutral atoms, they're making a lot of progress, and they're doing the same thing. They want to make higher fidelity and faster gates, right? Everybody wants to get to the upper right corner. There are other technologies like silicon quantum dots, NV centers, many of these technologies. It's also important to remember that it's not just the gates. We also have to initialize those qubits, and we have to read them out. And those have timescales as well. And those timescales determine what the clock is going to be of your future quantum processor. And you want that to be as fast as possible. So there are many outstanding efforts worldwide trying to build these, and you'll hear from some of the companies that are building them in just a few minutes. These are what quantum processors look like today. You can see superconducting processors from IBM and Google. You can see a processor, inside that big black box is a processor from Quera. There's one from IonQ and D-Wave, which is a quantum annealing machine. This, of course, is not a quantum computer. You'll recognize that as the Wright Flyer. And I put this on here because I think this is really the stage where we're at today. And what I mean by that is the Wright Flyer wasn't the first time that people flew. We often say that, but that's not true. There were gliders before this. There were hot air balloons before this. But when this all came together, there's a person who's steering it. That thing is heavier than air. It's self-propelled, and it flew. Now, it flew about 500 feet, and maybe only 10 feet off the ground. And they tried it several times that weekend. One time it crashed. They had to fix it, and they fixed it, and then they flew it again. They flew it again. And that's where our quantum computers are today, right? They're not very reliable. But when we saw this, we knew that commercial aviation was coming. It might be 10 or 20 years away, but it's coming. And I think when we see these quantum computers that you see here, we're at this stage. And there's a lot of hard work before us, but we know that commercialization is coming. But to realize the promise, we have to engineer quantum computers that are robust, reproducible, and extensible. This is my last slide. What that means is that the grand challenge for our field now is to achieve active quantum error correction. That is, that even though there are errors, that we can somehow detect those errors and then correct for them to make our error rates go down and down. And the reason it's important, you can see here that we're right here in terms of our physical qubit error rates, 1 in 1,000, 1 in 10,000 maybe. But for commercial applications, we need to be down here at 1 in a billion to 1 in a trillion, right? And that's a giant chasm, right? And we're not going to make up that difference by making better qubits. I shouldn't say that. That's very concrete. It would be unlikely that we're going to make up that difference by making better qubits. By the way, CMOS, it's 1 part in 10 to the 20. That's why these computers are so awesome, right? They almost never fail. If this fails right now, it's almost certainly going to be the software. It's not because one of the transistors had an error. And so the way that we overcome this is through quantum error correction, which is we take single qubits, put them together in groups, which we call logical qubits, and together they perform better than any individual. And you can think of this maybe as like a kindergarten class, right? If you have a class full of kindergartners, that's quite rambunctious, right? And total chaos. And if you add more kindergartners, it's not going to get better. There's going to be more chaos. But at some point during our education, we get to the point where adding people together actually makes the team better. And of course, by the time we get into jobs, that's how you do things. Very few individual contributors. It's all done by teams because the team acts better than any individual. And that's the concept behind quantum error correction. It did crash. Oh my gosh. Awesome. Right on cue. Thank you. Yeah, it did. It crashed.
Let me have to blank the screen for a second.
Yeah.
Give me 1 second. I'm just going to blank it.
Yeah. Oh no.
There it goes.
Wait,
All right, all right. It was just sleeping. It's like, God, is this guy done yet? So the point with quantum error correction is that you're going to have a team of qubits, and they're going to work better than any individual. But of course, you have to reach some threshold. You have to educate those qubits enough that adding more actually makes the situation better. But once you've done that, by the way, you pay a penalty, of course. You have to do more. I have to address 9 qubits instead of 1, right? Or 25 qubits instead of 1. But the advantage I get from the team is so much more. You know, I got to feed all those people, but what they're going to give back to me is so much more that it's worth it. And the goal then is to increase the size of your logical qubit, the number of physical qubits in it, to gain advantage. And you could ask how much advantage? Well, in fact, it's exponential. If you look here, here's the logical error rate, the error rate of the logical team, and here's the physical error rate of the individuals that make up that team. So even though the individuals are, look, 0.3% error or 0.075% error, we're talking exponentially here, 10 to minus 4, 5, 6, 7, 8, 9 off the screen. And you can see for these largest logical qubits, you're winning very fast. I decrease the error rate of my individual by a factor 2, but I gain exponentially in the overall error rate. And then that's where we want to be. That's what we need to demonstrate. So Google Quantum AI has demonstrated improved performance going from a distance 3 code, as we call it, to a distance 5. That's great. That's the right side of the line. You want to show that as you add more qubits, things get better. And there have been many other demonstrations from many other groups to show aspects of quantum error correction. Still early days, but this is what we need to do in the long term. Oh, sorry, this is really the last slide. Just some facts and myths, or maybe facts. First, quantum computers are not going to replace classical computers, at least for the foreseeable future. And in fact, you know, quantum computers operate in tandem with classical computers. We program the classical computer, then the quantum computer runs, okay? We need more algorithms, right? We talked about that. We need more algorithms. Quantum computers are not going to break encryption soon. To break encryption that we're using today, public key crypto systems, we're going to need very large quantum computers, millions and millions of qubits. So we're not there yet. Nonetheless, we need to switch over to what's called post-quantum crypto systems, which are crypto systems we believe are immune to attack by a quantum computer. And we need to do that now. You might ask, why do I need to do it now? I'm not going to have a quantum computer that can do this, decryption for many years. Well, the reason is you probably have information that you're encrypting now that you want to remain secure for 10 years or 20 years or 30 years. So we need to switch over now. And we're almost certainly going to need quantum error correction to be commercial. And there is a great science and engineering challenge. And so with that, let me thank you for your attention. I appreciate it. And have a great time over the next few days.